Which transistor will work with my project? Mouser alone lists 37,000 different types. We will reduce this number to a survival kit for our lab. To do that, we need a little background and do some experiments. Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. In this video we will focus on Arduino and ESP projects and switching applications. Look at the technology behind the transistors to distinguish the needed from the nice to have. Do some tests in typical applications. And finally provide some rules of thumb and a survival kit for our lab. As usual, I simplify a lot. If you are interested in transistors, you can buy this book. It has 150 pages on transistors alone, just for the theory. Transistors are basic components of all our projects, either as single transistors, in integrated circuits, or in our microprocessors. Everybody uses millions of them every day, most often without knowing. Their main purpose is to amplify and to switch signals. If we start with transistors, the most important question we have to answer is, do we want to build linear or digital systems? Digital systems, theoretically, only have two states, on or off. Linear systems typically are analog circuits like amplifiers, oscillators, etc. They also use all values between on and off. Because Arduino or ESP projects mainly use digital technology, we will focus on the digital systems, which makes it a lot easier. Let's start at a very good place, the catalog of Mouser. You can also start with DigiKey or other large distributors if they offer a structured catalog with filters. If we look at the first page, we see that unfortunately we cannot set a filter for the most important question. There is no filter for linear or for digital transistors. So we need to dig deeper. Let's look at the available transistor types. The most important are bipolar junction transistors, short BJTs, or field effect transistors, short FETs or FETs. Darlingtons and IGBTs are specialties which we will not cover today. RF means radio frequency, which is an analog area. We can cross it out too. You see, our list starts to get shorter. Because they were invented first, we will start with BJTs and later go on to the field effect transistors. If we select them, we still have a wide choice of nearly 8,000 different models. We see two types, NPN and PNP. The combined category mainly contains special types and wrong master data. We cross it out. To understand where we have to choose an NPN or where a PNP transistor, we can build a simple setup. An Arduino which has to switch a power LED. According to the datasheets, the Arduino or ESP pins only deliver milliampere, but our power LED consumes much more. Fortunately, we learned before that transistors amplify signals. The BJTs in particular amplify current, exactly what we need for this case. We use our 50-50 chance and select an NPN transistor, connect its base to an Arduino pin, connect the emitter to ground and the collector to the usual combination of an LED and a current-limiting resistor. A small base current should now produce a larger current through the LED. We can try it out and build a powerful blink sketch. It works. Cool. Was I just lucky with the selection of the NPN instead of a PNP transistor, or is there a rule of thumb? Fortunately, it's simple. The diode in the symbol of the transistor has to conduct to switch the transistor on, which means for NPN transistors that the base voltage has to be around 0.6 volts higher than the emitter voltage, which is the case if the Arduino outputs 5 volts when the pin is high. If I chose a PNP transistor, we would have to mount it upside down. Otherwise, the diode would never conduct. But we will see that this is not optimal. And we have to pay attention. We know that a conducting diode is nearly a short circuit. To show you the effect, I can use my new bench power supply from the last video. I connect a diode between plus and minus, select the 5 volts of the Arduino pin and switch it on. You see what happens. Not good. Of course, this does not happen with an Arduino pin. But something else can happen. Because the Arduino often is the weaker element, it might be destroyed. This is why we need a resistor between the pin and the base of the transistor. But how big should it be? We can make 2 assumptions. The diode from base to emitter has a voltage of around 0.6 volts. And the transistor amplifies the current by a factor of 50. Our LED will use less than 0.5 ampere. So the basic current will be around 10 milliampere. Okay, even for an ESP. The resistor is then 5 minus 0.6 divided by 0.01 equals 440 ohms. The standard value 470 is okay too. Done. Let's test it. I use an Arduino Nano because I do not want to kill a Uno. You never know. And a power transistor in a TO220 case. And really, it blinks. Quite bright. By the way, when the pin is high, the oscilloscope shows around 0.7 volts at the base, as expected. This is a good usage of an NPN power transistor. Why would we need PNP transistors? We can exchange the NPN with a PNP type. As we learned before, the diode has to conduct if we want the transistor on. In this case, we have to switch the transistor on by putting the pin to low or 0 volts. If the transistor is on, it should behave like a short circuit, and the voltage here has to be close to 0. Unfortunately, then, this diode does not have the needed 0.6 volts to switch on. So this is impossible, and we will get an equilibrium of maybe 1 volt. And the transistor will get hot because it has to dissipate the power created by this volt. If we put the transistor in a different place and connect the emitter to 5 volt, things change. Also here we need a base resistor. Now I have to confess, I only have a few low-power PNP transistors in my lab. The best I can offer is a 2N5401. Also here the LED blinks, but not as bright as before. The current is much lower because this transistor has a higher resistance. 3 parameters are important if we select BJTs for switching applications. The maximum collector current, the maximum voltage it supports between the collector and the emitter, and the gain. A quick check in the Mauser catalog shows that what we already know. We get transistors for very small currents and, if we scroll down, also stronger parts for up to 150 ampere. And up to 1.2 kilovolt. Not bad. Anyway, too much for me because I fear high voltages combined with lethal currents. But I deviate. Let's come back and assume we want to connect our LEDs to 12 volts. What happens to the NPN diagram? Nothing. If we increase the current limiting resistor of the LED, it will work exactly the same way. What happens with the PNP diagram? Let's do a test and increase the voltage slowly. As I said before, safety first. Strange, the LED does no more switch completely off. And now it stays always on. Not good. Did we already create the first casualties? No, it's quite easy. High on the Arduino is 5 volts. And if we go higher than around 6 volt, the transistor stays on whether the pin is low or high, because it has a negative base emitter voltage all the time. This is what we have to keep in mind if we want to use transistors on the so-called high side. Very good. Now we know all we have to know. NPN transistors work on the low side, PNP on the high side. And for high currents, we need power transistors. I forgot only a small detail. Because FET transistors are much better for switching, we do not need NPN nor PNP transistors in our lab. Only if we want to build linear stuff. This is, by the way, the reason why I found some power transistors in a bin. I used them to repair my linear power supply in video number 228. Did I steal your time? I do not think so. Why? Try once to go to your boss without a discarded alternative. He for sure will ask you, why did you not consider the other alternative? This is what I wanted to avoid. So we can go on to the Mauser catalog and key in our learnings. Only FETs. We still have MOSFETs and JFETs. Also here it's easy. JFETs are for linear projects. So we can select only MOSFETs. Shit! Still 20,000 different types. What a mess! Maybe it helps that we only have money for silicon transistors. I deselect all others. Unfortunately, not a big help. Let's also concentrate here on the polarity. We find N-channel and P-channel types, and also some specialties in between. We can concentrate on N and P-channel MOSFETs. Let's quickly check. Nearly 14,000 are N-channel and only 2,500 are P-channel. In Switzerland, this would be a clear vote. We would choose the N-channel. Let's look at the symbols of the two types. Unfortunately, we find many confusing symbols for the same type of FETs. If we choose the right one, the N-channel looks very similar to the NPN and the P-channel like the PNP transistor. Only the pins are named differently. Maybe the time at the beginning of the video was not completely lost. A closer look reveals another difference between BJTs and MOSFETs. The gate is not connected to the source nor the drain pin. It is completely isolated. Very interesting. If we remember, the Arduino, especially the ESPs, cannot source a lot of current. These transistors can not consume any current because the gate is not connected. Very helpful in this respect. But how should this work? Not connected things in our lab usually do not interact. Really? Do you remember the last video with the Tesla coil where the neon tube was on without any connection to anything conducting? The electrical field of the Tesla coil did the trick. Also here, an electrical field does the trick. A strong field opens the channel from drain to source. Without the field, the channel is closed. Very interesting. We can open and close an electric valve without applying any power, only voltage. Maybe you start to understand why we do not need BJTs in our labs anymore. Of course, you are not convinced, but I have a second ace. Let's check if we also get small and big transistors. Here we have to look at the maximum continuous drain current. Wow! Most of these MOSFETs are beasts compared with the BJTs. You hardly find milliampere, and you find tons of stuff above the 160 ampere of the strongest NPN transistor. And the maximum voltage across drain and source? You remember the BJT record was 1.2 kilovolt. Here we easily find parts up to 4.5 kilovolt. Still not convinced? What else do you want? I know. It should be dirt cheap and very small. But now you probably want too much. We already have parts that do not need any power to open and close the switch and are capable of handling the largest currents as well as the highest voltages. But maybe I have a third ace? Let's play and build the same thing as before. I take a decent N-channel MOSFET and connect it exactly as the NPN transistor. Because no current can flow into the gate, we do not need a resistor and can connect the gate directly to the pin. Power on, and it blinks as before. No big difference, and you would have to look at the printing of the transistor to see if I used an FET or a BJT. Do you remember my magic hands from the Tesla coil video? They also work here. I disconnect the gate from the Arduino and touch it only with one of my fingers. And the LED goes on and stays on. Is this cool? Unfortunately, it does not switch off when I touch the gate a second time. Here I have to train my magic hands a little longer to get this effect right. Really? No, of course not. As seen before, the gate is completely isolated. If I touch it with my hands, it gets a very small charge, which is sufficient to switch the channel on. Incredible! By the way, this charge easily stays there for an hour or so. Only if I connect the gate to ground, the LED is switched off. This is why you often find a resistor between gate and source. This incredible feature has an important disadvantage. Small charges can destroy the isolation of the gate. The FET is then ready for the wastebasket. So pay attention if you work with FETs. Never use carpets. Use such an ESP mat on your desk and connect your body with the earth with such a band. There is one more important thing we have to know. Most FETs need gate voltages of more than 5 volts to switch completely on. These transistors cannot be used with our Arduino projects, even more with 3.3 volt ESPs. Here we have to have a sharp eye to find the right ones. But how can we find them? Sometimes they are called logic level MOSFETs. This is an indication. And we can try to select VGS threshold voltage of less than, let's say, 2.5 volts in the catalog. The best way is to go to the datasheet and search for the diagram which shows ID in relation to VGS. Select the curve for 25 degrees Celsius and check where it starts. If it starts below 3 volts, this is an indication that it is a good choice. The IRF 540 I have used before is not a good choice, as we easily can see in the diagram. At the Arduino 5 volts, it conducts 20 ampere, but below 4 volts, nearly nothing. We can check this by connecting the gate to the 3.3 volt rail of the Nano. The LED is not very bright, a sign that the FET is not completely switched on. The FQP30N06L, for example, is a much better choice. It starts to conduct around 2 volts. And you see, it is no problem to use it for our 5 volt projects. So you only need FETs which are 3.3 volts compatible. Let's continue with the P-channel MOSFETs. They compare with the PNP transistors. The gate has to be negative compared to the source. Let's connect a P-channel MOSFET. As before, I use a small package, but much smaller than before. This time it is even an SMD, and I have to solder it on a PCB to get the wires connected. Let's switch the power on. The LED lights up bright as with this chunky power transistor before. Nearly incredible. And the SMD does not get too hot. Why is this? The power a transistor has to dissipate is calculated by this current and that voltage. The current is the same for both transistors. BJTs have a minimal VCE voltage, which creates heat. FETs act more as resistors. When switched on, the so-called RDS on can be extremely low. The power dissipated by a resistor is R times I square. I use an SI2301, which has an RDS on of 0.1 ohms at a VGS voltage of minus 4.5 volts. The dissipated power in our scenario is therefore 0.1 times 0.4 square equals 16 milliwatt. Not a lot, even for this tiny package that could dissipate 1.25 watts under normal conditions. Power dissipation is very important and always has to be taken into calculation when we deal with transistors, but also with linear voltage regulators, for example. If we use the part without the heatsink, we can get the maximum power dissipation right off the datasheet. Larger cases like this TO220 or this TO3 are made to be mounted on a heatsink. Then the calculation is a little trickier. I leave a link if you are interested. As a rule of thumb, typical makers hardly will have problems with the power dissipation of FETs in switching mode. I want to show you a nice trick with a P-channel transistor I used in video number 101. If we place a P-channel FET into the power line of our microcontroller, it can switch power off and on. If we connect a pin to the gate and the pin goes high, VGS becomes nearly zero and the MCU switches off. Unfortunately, we cannot switch it on anymore. But if we connect a push button across the FET, the MCU powers on. And if we switch this pin to low, before we leave the push button, it stays on. I used this diagram for an Amazon order button, where, after pressing the button, the ESP8266 powered on and sent a message to IFTTT. After that, it set the pin to high and switched itself off. Very handy. One last thing we have to consider. So far, we always switched slowly. Then the gate current really is close to zero. This changes if we start to switch faster, for example with a PWM signal. Why that? We already discovered before the capacitance between gate and source. Every time we switch the FET, we have to charge or discharge this capacitance first. To show you this process, I connect a 1 kilo ohm resistors between the driving pin and the gate. If we measure the voltage across this resistor, we can see the current flowing into and from the gate. Because I need higher frequencies for that test, I replace the Arduino with a signal generator. It creates the same pattern of 0 and 5 volts with a frequency of 0.5 Hz. The oscilloscope shows nothing. At least nothing visible. Only if we trigger it to a positive or negative signal and zoom in, we see the very short spikes which resemble a discharging curve of a capacitor. If we increase the frequency to, let's say, 500 Hz, we see many more spikes. 500 Hz, by the way, is the PWM frequency of the Arduino. Because of our 1 kilo ohm resistor, 1 volt on the screen is equal to 1 milliampere. Peak current for the moment is more than 4 milliampere. Not nothing compared with the theory. This is why it's good practice to add a resistor in front of the gate to protect your MCU pins from high currents. If we go up with the frequency to, let's say, 20 kHz, we see that most of the time the gate capacity is charged or discharged. This means that the gate voltage is no more digital as we assumed, and the average RDS is much higher than anticipated. And it means that the FET heats up. And as you see here, if we increase the frequency even more, the LED does no more get the full current. One last parameter can be important if you deal with higher voltages. Maximum drain source voltage. If your projects do not exceed 12 volts, you are safe with most FETs. If you go higher, please check this value too. So summarized, we learned that FET transistors are better than BJTs for general purpose switching applications. This is why we do not need any BJTs in our lab survival kit. N-channel FETs are used for the low side, P-channel FETs on the high side. This is why the bare minimum for our survival kit is 1 N-channel and 1 P-channel FET type. Especially if we work with 3.3 volt logic, we have to pay attention that we get them with a low VGS threshold voltage. Otherwise, they will not switch on. Because these types also safely work on 5-volt logic, there is no need for an additional type. As we saw before, for most of our applications, small SMD parts would be sufficient. But we also saw that SMD parts are hard to use for experimentation because they are too small. Best for handling would be a TO95 case. Unfortunately, you hardly get power FETs in such through-hole cases. This is why I mostly use TO220 cases for experimentation, even if it is a complete overkill. If you create PCBs and do not like through-hole components anymore, you definitely have to add at least 2 SMD types. If you go for SOT 223 packages, you might get away with only SMD parts, because you can easily solder wires to them. Or you decide on these small PCBs and use those for your experiments. Then you can also avoid TO220 cases. You find links to a few possible types in the description. They are not expensive. We managed to get from 37,000 transistor types to only 4. Not bad. And, as the third ace in my sleeve, they can be very small and dirt cheap. What do you want more? One last thing. Rumors say that many active parts on AliExpress are fake. I do not know if this is true or not. Sometimes I ask myself why they would fake something which is anyway dirt cheap. Please also keep in mind that the cutting and packaging of 10 transistors in the Western world easily cost more than the value of the chips. This could also be a reason for cheap chips in China compared to DigiKey or Mouser, even without faking them. So you decide what you want to believe. For sure, I cannot tell you if you get genuine parts with my links, but so far they were good enough for the girls I go out with. If you want to know more about your transistors, you need a transistor tracer like the one I recently built. These are my considerations on how to reduce the choice of 37,000 to 4 transistors. I'm sure you can add more to the topic in the comments, or you share your transistor survival kit with us. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the links in the description. Thank you. Bye.